Welcome back. In this lecture we will discuss Bayes' theorem. So we can look at the probability of a conjunction between two propositions H and E in two different ways. So the first would be the probability of H conditioned on E multiplied by the prior of E. And this comes from the simple fact that P, H conditioned on E, equals P, H, and E over P of E. But we also know that P of E given H, that is going to equal the probability of H and E over the probability of H. And notice here that the numerator in both of these is the same. So as a result, there are two different ways we could get to that probability of that conjunction. And here they are. Now, Bayes' theorem is combining both of these together in a single statement. Again, assuming that the probability we see the evidence is not equal to 0. And that's right here. And this is just simple algebra from the above. So what is this good for? Well, let's talk about that. Oftentimes we have causal knowledge. So the probability of observing a symptom given that someone has a disease. So let's say we have, a whole bunch of people that have colds, and only a subset of them have a high fever. And so we know that the probability of observing the fever given that they have a cold, and we can compute that directly based on that population. But what we're really interested in is the probability of having a disease given that there is a fever. So maybe someone has a totally different disease given they have a fever, and we want to determine if they have a cold based on that symptom, because we have medication especially for a cold as opposed to medication for, let's say, COVID-19. We can also think of the probability that a light is off given the status of switches. But we want to know the probability of the switches being in a certain status given that the light is off in some of the switch positions. Probability that the alarm goes off given a fire, and the probability that there's a fire given an alarm. So especially in the case where the alarm just might sound off for improper reasons. And we can think of a lot of examples of where this kind of thing can be useful, especially in fields such as cybersecurity. Probability that the image looks like a certain item, given that there is a tree in front of the car. And then probability that there's a tree in front of the car, giving, that an image is returned a certain way. So all of these, this is a wide variety of use cases, and they all can be addressed with Bayes' theorem because it relates this causal knowledge to evidential reasoning. So here is a classic problem, and we're going to walk through this one. A cab was involved in a hit-and-run accident at night. Two cab companies, the green and the blue, operate in the city. And we're given the following data. 85% of the cabs in the city are green, the other 15% are blue. The eyewitness identified the cab as blue. The court tested the reliability of the witness and the circumstances on that night and concluded that the witness correctly identifies each of the two colors 80% of the time and fails 20% of the time. So what is the probability that the cab involved in the accident is blue? And this is a famous example from Daniel Kahneman, Thinking Fast and Slow. Okay, let's walk through this. So here is what we have. We have the following conditional probabilities. The probability that the witness sees blue, given it's blue, is 0.8. And the probability that the witness sees blue, given that it's green, is 0.2. And we also have the priors of blue and green in there, 15 and 0.15 and 0.85. And what we really want to see is the probability that it's actually blue when the witness sees blue, because that's our evidence, is the witness saw blue, and we want to know the probability that it's a blue cab. And so here again, you can see right away we're going from some causal information, which is up here, to some evidentiary reasoning. All right, so how do we go about doing this? Well, by Bayes' theorem, so starting with the the evidentiary reasoning, the probability that it's blue, that the witness sees blue, is equal to the following. It's equal to the probability the witness sees blue given that it's blue, and we have that, times the prior probability of it being blue, divided by this prior probability that the witness sees blue. Information that we were not given. Okay, so we know that since the priors add up to 1, the cars are going to be either green or blue. So we know that the probability that the witness sees blue has to equal the sum of these two sets of worlds. You have the probability the witness sees blue and it's blue, and the probability the witness sees blue and it's green. Okay? So the witness sees blue, it's either going to be one of two things. It's blue and it's blue, or the witness sees blue and it's green. That's it. There's no other opportunity. So those two items have to equal to the probability that the witness sees blue. So as the probability the witness sees blue multiplied by PB, we can compute this directly as 0.12. And so this also comes directly from the definition of conditional probability. But here we're using the information on the probability that the witness sees blue multiplied by the prior of seeing blue, and that equals the conjunction there. So now we can do the same thing for the green side. Now this is the probability that the witness sees blue conditioned on green multiplied by the probability of green, and we get that is equal to 0.17. So therefore we just got to add those two together, and we get the probability that the witness sees blue, and that's 0.29. And so if we round to the nearest thousand, we can combine all these together to get probability that it's blue, that the witness sees blue, and this would be probability the witness sees blue given it's blue is going to be 0.8 times the prior of blue, 0.15, and that's all going to be divided by 0.29, and the answer to that is going to be 0.414. So that's it for this introduction to Bayes' theorem. Please stay tuned for more content.